And so the two critical points are 1/3 and 1. If we put these on the number line, then we can test some values to the left, in between, and to the right. So if we test a 0 back in the first derivative, we would get 3 times 0 minus 1 times 0 minus 1, which would be -1 times -1, which is a positive. So everything to the left of 1/3 would be positive. If we test something in between 1/3 and 1, maybe a 2/3, then we have 3 times 2/3 minus 1 times 2/3 minus 1. This would be negative, this would be positive, so the product would be negative. If we test something to the right of 1, say a 2, then we would have 3 times 2 minus 1 times 2 minus 1, which would be positive. So according to this, you would have increasing from -infinity to 1/3 and from 1 to infinity, and decreasing from 1/3 to 1. They ask us for the maximum and minimum. So the maximum would be where the first derivative changes from positive to negative, or at 1/3. And our minimum would be at 1, where it goes from negative to positive. Now if we wanted to find the actual y-coordinate for these, we would need to put these back into the original and get the y-coordinate. So 1 minus 2 would be -1, plus 1 would be 0. And then 1/3 is a little harder.
Yeah.
Okay, so we need to figure out the y-coordinate that goes with an x-coordinate of 1/3. So I'm going to put my function into the calculator. Then I'm going to go to my table and plug in 1/3. So it's about 0.15. For our maximum. Now we need to take our second derivative, which would be 6x minus 4. Set it equal to 0. And we get 2/3. So that's our possible point of inflection. We put that 2/3 on the number line, putting it back in the second derivative, and we test. If we test a 0, that's going to be negative, and if we test something like a 1, that would be positive. So that means it's going to be concave down from -infinity to 2/3, and concave up from 2/3 to infinity. Now if we take the critical numbers that we had from the first derivative and we put them into the second derivative, then that will also tell us something about the maximum and minimum. But we already found those with the first derivative, so we'll go ahead and then write down the point of inflection, which is 2/3. We'll get our calculator and figure out what we would have if we put a 2/3 in for x. And it's about 0.07. So the point would be 2/3, 0.07. So we've got the critical numbers, we've got the max min, we've got the second derivative, the concavity, and the point of inflection. So that's number 41. Now we want to do number 49. Okay. So this one is the same idea. Here we have x to the 5/3 minus x. So we take the first derivative, which will be 5/3 x to the 2/3 minus 1. Figure out the critical numbers. By solving. So if I multiply both sides by 3/5, I'll get this. And then we could cube both sides at this point. So if we cube that, the 3's cancel and we just get x squared. And here when I cube it, I get 27 over 5 cubed, which is 125. And then I take the square root of that to get what x would be, and it's going to be plus or minus, and we'll get an approximation for that. And it's approximately 0.46. So plus or minus 0.46. We can put that on the number line as our critical numbers, negative 0.46 and 0.46. We've got our first derivative. If we test the easiest one, of course, is to test what's in between, which is 0. And here's our derivative, so 0 would give us negative values. Something to the right, a 1, would give us a positive value, and a negative 1 would give us a positive value also. So that means we have a max at negative 0.46, and you can plug it in to get the y, and we have a min at positive 0.46. Now we take the second derivative. A little tougher because we have to take the 2/3 times the 5/3, which gives us 10/9, and then decrease the 2/3 by 1, which would be negative 1/3. And then the derivative of 1 is just 0. So we set that equal to 0. And the only way that this could equal 0 is if x is 0. So we put that on our number line, and we test. If we test a 1 back in the second derivative, that's going to be a positive. And if we test a negative 1 to the left of 0, cube root of negative 1 is negative 1, and then negative 1 to the negative 1 power is the same as negative 1 over 1. So that would be a negative value. So that means it's concave up from 0 to infinity. It's concave down from negative infinity to 0. And the point of inflection is at 0. We plug that in the original, and we get 0. So that gives us everything we needed for number 49. Now we need to move on to the L'Hopital's rule that we did today, and look at the homework from that. So on page 229, you had number 1, and here it says, use L'Hopital's rule to evaluate the limit or state that L'Hopital's rule does not apply. Remember, you have to have the indeterminate form 0 over 0 or infinity over infinity to be able to use L'Hopital's rule. So the first one is the limit as x approaches 3 of 2x squared minus 5x minus 3 over x minus 4. Well, we cannot use L'Hopital's rule here because when we plug the 3 in the denominator, that's the easiest place to plug it in, we don't get a 0. We can figure out the limit, but L'Hopital's rule does not apply. So moving on to number 6. So the first thing we need to do is to plug the 3 in. When we plug it in the numerator, we do get 0. And when we plug it in the denominator, we also get 0. Which means that we can use L'Hopital's rule. And we would take the derivative of the numerator over the derivative of the denominator. And then we try to plug the 3 in. So when we plug the 3 in the denominator, 3 squared is 9, times 3 is 27, minus 7 is 20. And when we plug the 3 in here, 3 plus 1 is 4. The square root of 4 is 2. 2 to the negative 1 is 1/2, times 1/2 is 1/4. So that ends up being 1/80. So we can't evaluate with L'Hopital's rule on that one. Number 11 was the limit as x approaches infinity of 9x plus 4 over 3 minus 2x. Okay, and what happens here, if we try to plug the infinity in, you can't really plug infinity in, but you can talk about what happens as x gets larger and larger and larger. Okay? And so this numerator would get larger, and the denominator, this is going to be 3 minus 2 times a number that gets larger and larger. So that one's going to go to probably to negative infinity. So we can use L'Hopital's. So the derivative of the numerator is 9. The derivative of the denominator is negative 2. So this limit is just negative 9/2, or negative 4.5. The limit of a constant is a constant. This you should also recognize is actually the horizontal asymptote of this function, 9x plus 4 over 3 minus 2x. Moving right along, number 17 is the limit as x approaches 1 of square root of 8 plus x minus 3x to the 1/3 over x squared minus 3x plus 2. I believe that's a square. Yeah. So if we put a 1 in there, we are going to get 3 minus 3, and we put a 1 in the denominator, we get 0 also. So we would use L'Hopital's. And so the derivative of the numerator would be 1/2 times 8 plus x to the negative 1/2 minus 1/3 times 3 is 1, x to the negative 2/3 over 2x minus 3. So if we put the 1 in there this time, in the numerator, we'll have 8 plus 1 is 9, square root of 9 is 3, 3 to the negative 1 is 1/3, times 1/2 is 1/6, and then the cube root of 1, well, 1 to anything is going to be 1, so that's going to be minus 1. In the denominator, 2 times 1 is 2, minus 3 is negative 1. So we'll have negative 5/6 over negative 1, which is 5/6. So that would be evaluating the limit using L'Hopital's for number 17. Number 21. Limit as x approaches negative infinity of 7x squared plus 4x over 9 minus 3x squared. Again, you're going to get L'Hopital's rule. The requirements are met. So we just take the derivative of the numerator, which is 14x plus 4, over the derivative of the denominator, which is negative 6x. But we notice that we get L'Hopital's rule requirements again. So we have to use L'Hopital's rule again. Derivative of the numerator is 14. Derivative of the denominator is negative 6. So your answer is negative 7 over 3 for that one. So you had to use L'Hopital's rule twice on that one. 25. Limit as x goes to 0 of sine of 2x over the sine of 7x. L'Hopital's applies because you have 0 over 0. So the derivative of the numerator is cosine 2x times 2. Derivative of the denominator is cosine 7x times 7. So when we put the 0 in at this point, cosine of 0 is 1. 1 times 2 is 2. Cosine of 0 is 1. 1 times 7 is 7. So this limit is 2/7. Number 31. The limit as x goes to 0 of cosine of x plus pi over 2 over sine of x. 0 over 0. So we'll take the derivative of the numerator and the derivative of the denominator. So the derivative of cosine would be negative sine of that same thing, x plus pi over 2. And then the derivative of the sine is the cosine.